Good morning, ladies and gentlemen, and welcome to this morning's panel titled Graphene for the Automotive Applications, Lighter, Stronger, Better, Part 2. Before we begin, I wanted to go over a few logistical items. First, this panel session is scheduled for 45 minutes. Second, we invite the audience to submit questions through the text feature of this webcast located in the lower part of your screen. We may not get through all your questions, but we will certainly do our best to get through as many as possible. If you are having any technical difficulties, please refer to the help desk on the bottom of each page. For maximum bandwidth capabilities, please place all your local smart devices and other laptops in sleep or airplane mode. This should help with any buffering issues. Now, it is my privilege to introduce to you our panel moderator, Terrence Barkin, Executive Director for the Graphene Council. Under Terrence's leadership, the Graphene Council has become the leading global organization promoting the adoption of graphene-enhanced advanced materials on an industrial scale. Ladies and gentlemen, Terrence Barkin.
Thank you, Frankie. Good morning to everyone. Thank you for joining this session about graphene and use in automotive applications. I'll speak just very briefly about the Graphene Council as the host of today's session and the moderator for today. The Graphene Council was formed in 2013 and today reaches more than 27,000 material scientists worldwide that are working on graphene, researching it, or using it in applications. And in particular, the automotive sector offers tremendous opportunities for this nanomaterial. To give you an idea of some of the members that are in the Graphene Council, we have the entire ecosystem that includes researchers such as the University of Manchester, where graphene was first discovered and for which two of the scientists were awarded the Nobel Prize in 2010. We have graphene producers from all over the world, and today is no exception. We have Mark Thompson, who is the Managing Director of Talgo Resources all the way from Australia, and Dr. Adrian Potts from the UK, who also has an operation in the United States with applied graphene materials. Both of these gentlemen will be speaking to you about applications of graphene in the automotive sector. The next slide, please, Frank. The interesting thing about graphene as a nanomaterial, and this is a piece of pure carbon at the atomic level, is that we've identified more than 40 major applications. And so when we look at automotive sector, we can look at energy storage, coatings, structural materials, composites, sensors, and much, much more. And so we'll talk about just a few of these applications today. And the next slide, please. Graphene, as I mentioned, was isolated first in 2004. Nobel Prize was granted in 2010. And since then, it has kicked off a flurry of research and patent filings, of which there were more than 2,000 in just the past year. Where we find ourselves in 2020 is that graphene production has reached the ton scale, which is enormous for a nanoscale material. And we now see it being used in automotive applications, and most notably, the Ford Motor Company has graphene-enabled parts in their production vehicles. And the next slide, please. So with that, if you have an interest in graphene and would like to learn more, the Graphene Council has tremendous resources, including the Graphene Report, which is more than 600 pages on graphene production methodologies, applications, market pricing information, standardization, and a review of more than 200 graphene producing companies worldwide. And with that, let's close this short introduction to the Graphene Council. And I'm very proud to introduce Dr. Adrian Potts, who is the Chief Executive Officer of Applied Graphene Materials. And that will be followed by Mark Thompson, the Managing Director of Talgo Resources. We'll take your questions, please, written. And then we will moderate a Q&A after both presentations have been made. So Adrian, it's all yours. Looking forward to hearing from you.
Thanks, Terrence. And can you see this in full mode just to check?
Not yet. If you.
Okay, okay, there we go.
All good. Thank you.
Great, thanks. So thanks, Terrence, and hello to everyone. It's great to be able to be with you today. So just to touch on myself, so as Terrence mentioned, CEO of Applied Graphene Materials. We're headquartered in the UK. my background is a career in materials engineering, and I've spent the last 5 years looking at graphene, particularly here in the North America, looking at business development opportunities for that, and then latterly working as CEO of the company. So graphene, remarkable material, remarkable performance. Graphene's been hailed as a single layer material, as Terence described it, at the atomic level, for amazing performance, whether mechanical, electrical, thermal, lubricity, permeability, and transparency, and all of those properties lend really well to a range of automotive applications. Our challenge as producers and as integrators are really geared around how to realize that performance in a practical way. So part of that is taking that single layer concept material and then translating that into a practical solution. So what we call graphene nanoplatelets, which are literally that small platelets of graphene material that we can then integrate into usable applications. As mentioned in the Graphene Council quote there, it's then really a matter of matching the right material, the right price point to the specific application and the specific objectives. So correct material for application, the value stream opportunity, understanding that is so important, the potential performance objectives, and really how to get from what is quite a challenging material to use into a usable form. So the strap line at the top of this slide, if you can basically get graphene into a material correctly, then you can make great use of the material advantages. The keys to that really are twofold in our view. A clear understanding of the application technology and the end use that is so much geared around a clear understanding from the end user about what they want to achieve, rather than just a look-see about what graphene might do. So clear understanding of objectives and end use goals, and then how that material might integrate into their system. And then we're great proponents of the how-to, backing up what we do with large amounts of test data, and also clear understanding of how to disperse materials well into appropriate materials, how to do that to create stable dispersions, how to add materials correctly, how to make sure that we have the correct chemistry for the end use application, the correct carrier for this nano powder, and ultimately the correct loading of material into the end use application. So our sweet spot that we have been operating in, that we'll talk to a little more today, is in the area of coatings, composites, printing, and thermal adhesives. So 3 areas for us just to cover in this briefing: graphene in composites, graphene in thermal applications, and then latterly in coating. So first to composites, and really just to look at the current status from our side of graphene in that application. So basically what we're doing here is taking graphene nanoplatelets, we're adding those to appropriate dispersions that are compatible to the end use. In this case, on this slide, what we're doing is taking graphene, dispersing it into epoxy carriers to enable them to be integrated into what we call carbon fiber prepreg materials. So these are high value, high performance, continuous fiber materials, such as are used typically in motorsport and in high-end automotive applications. Earlier demonstrators for that are clearly body parts and lightweight structures that can incorporate both carbon fiber and graphene. So early wins for us in this type of application. We're clearly in the area of improved mechanical performance for composite materials. So enhanced fracture toughness, as well as maintaining things like surface finish. So you see here a demonstrator part that we produced a number of years ago in tandem with W Motors as a demonstrator for manufacturability of graphene in prepreg. This material's commercially available in a pre-preg form, typically produced by a company called SHD Composites in the UK and the US. So commercially available material for enhanced fracture toughness and things like outstanding surface finish. So high performance materials in pre-preg form. Secondly, another area of application for composites where we've really done well is with one of our customers, Infinite Composite Technologies, here in the United States. And I put this up really to demonstrate the outstanding performance advantage that graphene can bring to these types of structures. So in this case, cryogenic vessels, it happens to be for space applications. The key message here, though, really is that with a graphene addition, compared to standard material, we're able to pretty much eliminate microfracturing of the resin material in extreme cryogenic testing. The read across to that is clearly evident. So why pick this example? Space applications have the potential to read across into more mainstream automotive applications for areas like pressure vessels, for areas like hydrogen-powered vehicles. And again, it's all about the correct format of material dispersed in the correct carrier material to enable the enhanced performance of the finished product. Thirdly, just to note, we're currently engaged with a tier one automotive supplier here in the United States, materials for high volume manufacturing of composite parts. The same message really is true. Put graphene into the appropriate to use materials, and you can really enhance the performance of the composite structures that you're trying to make. So comment here from the customer, really about direction of travel more than anything else. So we see positive directional improvements in the key mechanical performance of their composite systems that they're interested in. And encouragingly, no negatives either. So other mechanicals didn't show a significant decrease in performance. So areas of improvement, significant improvements in tensile strength and modulus, in flexural strength and modulus, and most importantly, in impact performance with those materials. So when we look at alignment to trends in vehicle technology, clearly there's a great opportunity, we feel, for improvements in mechanical performance, particularly as related to enhancements in resin systems. That clearly reads across into chassis, body panels that might be used, made from composite materials technology. And then in areas, specialty areas like pressure vessels, for mass transit, and with a particular eye to the Asian market. Just to touch on other technology, we do have a printing technology where we are able to take graphene and print that, our experiences into composite materials. But we believe that there is some great read across potential into other areas as well. If you can print graphene into composites and achieve great mechanical performance additions, currently we're doing this printing dots of material, but there's a clear opportunity to be able to print continuous tracks. So the read across into vehicle opportunities is potentially around continuous tracks of material, conductive graphene material, potentially to be able to save weight around areas like wiring for potential applications like LED lighting in vehicle technology. So graphene, great potential in this arena for composite and related applications. Secondly, in thermal applications, so here we have again been developing our platform in aerospace materials, looking at high conductivity and low density additives for composite for materials into this application. Currently, we have products in the market commercially available that are 2-pack thermal adhesives, around a 6 watt per meter K performance, but the advantage for aerospace is very low density, which again has the potential to read across into other applications. Good adhesive performance and things like low outgassing as well. So looking ahead into automotive, our question really is, could graphene figure in the automotive space for things like thermal interface materials, the need in respect to particularly battery technology, a technical solutions needed, as well as a volume anticipation for the growth of EVs and the growth of thermal interface materials. As you see on this chart, the top right, EV projected growth, and there are plenty of projections for EVs, and then middle left, the forecast growth from the ID TechX group for thermal interface materials in electric vehicles. The NREL put out their guidance on need for control of battery temperature, which we see there top left, and clearly there's an opportunity for graphene to be able to be used well in those types of application, again with the correct dispersion and the correct particle formatting. If we look at the current market and range of materials performance for those types of applications, we sit sort of in the middle of current thermal paste adhesive product offerings, so at around 6 watts per meter K. Typical products out there around 0.5 to 12. We believe there's great performance advantages to be gained in materials engineering and materials engineered solutions. So things that we're looking at currently, looking at controlled alignment of graphene to be able to create planar structures with that material to enhance thermal conductivity further, as we see in the middle of the top right little diagram, and then segregated networks or domains of materials, whereby we can actually segregate areas of graphene for higher thermal conductivity. And then also engineering to produce hybrids also, so combining with other materials to enhance the performance yet further. So we see a great need, but we see a great opportunity also for graphene in this space to be able to contribute through materials engineering to create some great solutions for thermal performance with graphene nanoplatelets. And then thirdly, our third area, just as a brief overview, is in the area of coatings. AGM, we believe we've done all the hard miles in this area in terms of graphene application and graphene dispersions that are now pretty much optimized for paints and coatings. Our area of excellence is principally in primer applications and both solvent and water-based systems. Graphene works incredibly well when formatted in the correct way for both anti-corrosion, for barrier applications, for chemical resistance, for paints and coatings. I mentioned primer is our key area of activity, but when we look at tie coats and top coats also, clearly the materials can be integrated into those systems as well. I mentioned solvent-borne and waterborne coatings and a range of different chemistries, typical of what you might expect from a graphene addition to a paint and coating system, is seen here in the middle image, the visual image of highly effective corrosion performance for an automotive primer. This is a commercially available automotive primer with a 0.1% solids addition of graphene to that material. So you see this after a 3,000 hour anti-corrosion salt spray test. Image on the left, the current control base material. Image on the right with a 0.1% graphene addition to it. Commercial products available in aerosolized and available for spray shop applications, and then other areas for anti-corrosion performance in more elaborate systems where we're able to take the active out, so zinc and other actives, chromates and so on, to create more environmentally friendly corrosion performance products. Touching on where the industry is heading, water-based coatings are clearly the big win for the industry. We're able to add graphene very effectively to water-based coatings, and you see the little bar chart on the left-hand side here for blasted and abraded steel. performance advantages are outstanding, with very, very low loadings of graphene, ranging from 0.025% out to a 0.1% loading with the progress of those bar charts. You see the visual in the middle of water-based coating, where creep performance, so the creep of corrosion around intentional damage to a coating, is managed incredibly well. And then we see the barrier performance on the right-hand side of this slide with the graphene addition. Dramatic change to water transmission rate through a coating. And we're also able to manage color with very low graphene additions. So for things like direct-to-metal coatings, there's a great opportunity there. Lastly, really in this area, looking at automotive interiors, we see great potential utilizing the barrier performance of graphene in this area. Interiors tend to be a darker color, but we can utilize the barrier performance to really look at balancing chemical resistance and UV degradation. So graphene has plenty to offer in this space in terms of diffusion control, barrier, and deterioration from moisture and UV. Lastly, when we look at the future, really it's about use and abuse, we feel, and the need for greater expectation from coatings. Usage intensity increases, the trend to more water-based coatings, low VOCs. We see great opportunity for graphene in these applications, opportunities for smart coatings, for sensor coatings, and for powder coatings. So in summary, in answer to the question, lighter and tougher and better and stronger, we see great potential for graphene in the area of composites. We're now at a point where process method is pretty much agnostic, so graphene working in a range of different process methodologies. Potential in specialty applications for thermal, and some great performance advantages in coatings applications as well. So with that, I'd just like to say thanks for listening. A very brief tour to what we're doing and some of the application, the exciting opportunities where we feel graphene has some great traction. It's all about application technology, as I mentioned before, know-how, how to, and providing material solutions that work. So thanks for listening, and I'll hand you back to Terence.
Thank you, Adrian. Really appreciate that. And I think your presentation demonstrates the flexibility and range of performance that graphene can bring. And now we're going to hear from Mark Thompson from Talgo Resources, who's going to focus in on another application area that has tremendous promise, and that's in energy storage. Obvious application for the automotive sector. We saw from Adrian that the thermal management properties of graphene can help, especially for EVs and light weighting, which is also important in that sector. And now we're going to hear about the energy storage devices themselves and batteries. So, Mark, we'd love to hear from you about that. And as you're teeing up your slides here, we'll just wait till they get to the full presentation mode.
Yep, no worries. Thank you.
And we appreciate you joining all the way from the other side of the planet.
Oh, no worries. The wonders of modern technology will never cease. But
awesome.
No, pleasure to be here. And I've chosen definitely much to focus on the better part of the lighter, stronger, better section of graphene. And Talgo, we're a vertically integrated graphene company, so we make the graphene from scratch, starting from graphitic precursors in the ground in Sweden, and we deliver fully functionalized applications of graphene as products for our customers in a whole range of things, building products, composites, likewise coatings. These are all very exciting sectors that we work in alongside our colleagues. And today we're just focusing specifically on batteries, so energy storage. And as you heard earlier, graphene is it's a strange form of graphitic carbon. I know it's graphitic carbon. We know that it's the component of graphite, but mankind has not had, and more specifically engineers have not had access to this ultra thin form of it before. And it's only recently now that you're getting economic ways of making it. Talgo's been working with producing graphene since about 2014 now. And we are certainly, along with a whole ecosystem now of graphene producers, starting to get traction and get real results in the sort of materials that are being tested. So today I'm talking about next generation lithium-ion batteries, not entirely today's, but more like where things are going, the next step, something that's underway. So in the world of electric vehicles, one of the big problems is range anxiety. How far does the car go? And this, of course, is symptomatic of not only the weight of the vehicle, the friction of the tires, a whole bunch of components, aerodynamics, but the biggest component is the energy capacity of the battery. And for those interested in batteries for electric vehicles, you might know of or heard of the silicon. And silicon is a very interesting material. When you look at the electrodes of a lithium-ion battery, and on the cathode side, you have a whole bunch of different materials. The anode of a current lithium-ion battery is predominantly it's 100% almost graphite. It can be synthetic or natural graphite. It's usually a blend of the two. And what's interesting about that is that when you charge that material, when you charge your battery up and you're pushing electrons into your anode, you're causing it to swell. It swells by about 10%. Silicon is something that you can also push a much greater amount of lithium into. In fact, it can store 10 times the amount of energy over standard things today. However, at the moment, you can't use much silicon, and I'm going to explain why, and I'm going to talk about how graphene can help solve that. So if you want, I guess, a rough comparison, some numbers, graphite battery today, the capacity milliamp hours per gram of a graphite anode tops out at about 370 milliamp hours per gram. You could technically have over 3,500 milliamp hours per gram if you use silicon. So what's the problem? The problem is on many different fundamental issues. Silicon, actually, when you put an electric charge into it, it holds more lithium ions, but that also means it changes the volume by 300%. Now, if you've got a battery in a steel case, that is still going to cause problem. If you've got a battery in a pouch cell, or you're trying to engineer a battery pack for a vehicle, that swelling, that volume change is a killer in the physical application, but it's a killer internally. It leads to the very, very rapid death of the battery. What happens is the silicon particles themselves will pulverize and break under that volume change, and they won't go back in together. The entire particle system will try and lift off of the copper current collector. And more importantly, when the particle breaks, they increase their surface area. And that extra surface area means more lithium gets sucked out of your electrolyte and your cathode to form the solid electrolyte interface, which is the thing that coats the particles the instant you charge a battery for the first time. So once that lithium's gone out of the system and it's now stuck in a solid interface on the anode particles, you can't get it back. So you just lost, say, 10 to 20% of your battery capacity, which means you just lost 10 to 20% of your range in your electric vehicle, approximately. So this is the problem with silicon. So these are profound problems with if you want to get better performing anodes in the short term. So don't worry, we can fix it. Graphene can help solve this problem. It's been actually a problem for many years that has stumped many companies. And what we work on, amongst other things in our battery products, is that we've worked out that an ultra-thin coating of graphene, which can coat the silicon particles, can help to form a protective coating and different nanostructures that can sort of control that pulverization as the silicon breaks down. And so it can help retain and stop the volume change from happening so harshly. It means you can set up the pathways for the lithium to intercalate into the particles without blowing it up, and you can decrease the amount of the solid electrolyte formation. So this is a relatively recent development. We've got a picture here of Samsung as their version of it, but there's many others. And on this page here, I'll show you one of our products we've developed, which is called Talnode SI, which is our sort of registered trademark for this graphene silicon composite. So what you have now is a highly engineered porous graphene silicon composite. It's nanoscale particles now agglomerated and put together in a special way. And we do it using mechanical methods, not trying to crystallize things from gases. You have to, as earlier on, someone was talking about, of course, the Ford using composites. If you walk into Ford, I think they'll tell you about the limit for how much per pound of material they're willing to pay. You have to come up for us, we're very aware of the economics and making sure that these particles can fit into what would be a standard industrial framework. So we use off-the-shelf equipment, and the technology we focus on is always filtered through the economic cost. These particles now have Coulombic efficiencies of nearly 100% and very high first cycle efficiencies. And just to sort of summarize then, what's the end result? Well, today, down the bottom of this graph, you have graphite with no silicon at about 350, 360 milliamp hours per gram capacity. And as you sequentially add more and more silicon, you can see on this graph that by the time you add 80% of our combined graphene silicon product, you have nearly 3 times the capacity, which would enable much longer range of the vehicle, or you could design a smaller battery because now it's got more energy capacity, and that saves weight, which will have other massive impacts on the braking, the sort of design you have around the brakes, and all the other components of the system. So that was it. Trying to just be short and sweet on just probably a relatively little known use of graphene deep in the heart of batteries, which, to be honest, even today, silicon, as I said, is getting used more and more in anodes, but it's topping out at about 3 to 5% because of these problems. And we see graphene as a fantastic way of being able to now get the amounts of silicon up and give consumers not only better products, better performing products, but more sustainable products. And the interface between the consumer and the graphene producer, in this case, could well be yourselves. So at that point, I'll leave that and look forward to any questions.
Excellent. Well, Mark, thank you so much for that. That's absolutely fascinating. I think that's increasing energy density, especially for EVs, and keeping the weight under management is kind of the holy grail for the next phase of transportation, not just for passenger vehicles, but of course also for freight. And if we go back to Adrian's presentation, and in particular in coatings, and I know this is also an area that Talgo is working on, if you think about anti-corrosion resistance, or if you think about the shipping industry, with 80% of the world's global trade by weight is by ship. That's another interesting area that graphene has an application for, with anti-biofouling, or making the ships more efficient and reducing their fuel costs, which is their biggest cost factor. So my first question, let me go to Adrian. One of the big questions that's come up, because a lot of people have heard about graphene for many years. We had a hype cycle, if you will, and many engineers were kind of put off by the high cost and not figuring out how to be able to use this in a cost-effective way. And in your presentation, you showed load factors that are in the tenths of a %. Can you just talk about maybe the dichotomy of graphene being one of these materials that sometimes the less you use of it in certain applications, you actually get better results, and how that impacts the economics? Do you want to address that?
Yeah, sure. So, going back to the kind of performance attributes of graphene as a material, you're right. There was, in the early days, a lot of hype about that in terms of amazing performance. And as I sort of tried to portray, how you actually realize that performance. So, as Mark mentioned also, the economics of manufacture clearly come into play. What we have really discovered is taking that remarkable performance and being able to translate it in a cost-effective way into realistic applications. So, as you noted, Terence, the actual utilization of graphene into real applications. So you talk to coatings. Yeah, I mean, we're seeing outstanding performance of anti-corrosion attributes for coatings, barrier performance, at way, way low performance loading. So as I mentioned in that waterborne coating slide, 0.025% by weight of solid of graphene into that application. In composites, we're in the sort of 0.5 to 1% by weight loadings for mechanical performance. And then when you combine that with the barrier performance that graphene brings into some of those applications as well, it's a great result. So when you actually add graphene to a master batch, for example, maybe a 20% loaded master batch, and then that's then diluted into the end use application, we see the cost is not prohibitive.
So let me ask you just one more question before I go to Mark, and we'll talk about the energy storage. The other aspect that I think is important when anybody's introducing a new material is concerned about, do we have to have a different process? Do we need specialized capital equipment for this? How does it affect the host matrix, right? Viscosity issues, those kind of things. Can you just talk about using graphene as an additive into existing formulations and some of these issues I mentioned about the need or lack of a need for specialized equipment?
I would say that's everything. So our appreciation of the challenges of integrating a new technology is all about making it easy for the end user to be able to use that material. If you have to buy a boatload of specialty equipment, you're never going to integrate it. So our whole focus is on easy to use dispersion technology. So if you look at our paint additives, for example, they are stir-in additives, they are stabilized. So you want to be able to take that product. If you have a 55-gallon drum of this material, you don't want the graphene to sediment out. For example, if it's on the shelf for 3 months, you want it to be the same on the day you received it as 3 months down the line or 6 months or whatever. Same in the world of composites when we're taking graphene dispersions and adding them to composite resins. We want to do that in the most effective way. So, we have a standardized range of products that are available, as well as the ability to customize to suit a specific chemistry. So either way, our objective all the way through is to make this stuff easy to use, easy to integrate as a stirrable in additive, basically, to make it work.
Well, and the obvious observation here is how far graphene has come, because you have commercially available product that's actually being used for different coating systems, including a lot of metal coating applications. So I think it's really important that engineers have a second look at graphene if they've had some prior experiences that didn't meet expectations. It's a completely different world today. If I shift now, and thank you, Adrian. If I shift now and I go to Mark, again, this is fascinating. The giant prize in the world is this increased energy density in energy storage devices. And as you mentioned, silicon has had this expansion, contraction, and fracture issue for a long time. So congratulations on the achievements that are being made in that side. Having interfaced with the battery manufacturing sector, as well as the composite side, but the battery manufacturing sector seems to be incredibly conservative, and they're concerned about changing chemistries. Can you just talk about if an automotive company wanted to take advantage of this tremendous advance in energy storage, how would they go about getting this into their vehicle?
Well, first of all, of course, not many automotives do batteries. Some are vertically integrated, not many. But the ones that do, in our experience, it's really not much different to the standard anode development or battery development, which is they physically test it. It's not entirely modeled on specs. They want a sample, they get kilos of samples, and they test it, and then they see how it goes, and they modify it and try and optimize it, and it goes on from there. And I've got to say that it's probably because silicon's more of a new, it's quite heavily in use in some electronics manufacturers for smaller batteries with less cycle life than automotive. But focusing on automotive is like halfway to aerospace, right? It's very, very long cycle life and very big warranties. So the testing process is normally just one of physical sampling, and it's about a 2-year qualification process for normal materials. And for, I'd say, slightly newer material like this, where there's a lot more optimizing to be done, particularly in then it's maybe a little longer. But the responsibility of us is we try and set those materials up, the graphene material, to just be a drop-in solution, so that they can just mix it in, try it with you can blend it with your other materials that you like, and you've got full autonomy to treat it as a sort of totally separate product. And this is where it's very similar to the composite and sort of coating story and what I think it's still poorly understood about graphene, because unfortunately the early days media hype was that graphene is a thing, like a giant sheet or an object, or that it's this, you can go buy a tub of it. That's not the case, of course. It's an additive story. And the beauty of additives, as you were alluding to earlier, is very small amounts, but they've got massive leverage effects. And so the extra cost per unit, in this case with a battery, it's per unit of kilowatt hours per kilogram of the weight of the battery. That can be extremely low. It has almost, it's very little effect on cost. Likewise with polymers, at 0.25% loading of graphene, might sound bad if it's like $50 or $75 a kilo, but you're adding 15 or 20 cents US per kilo of the plastic component for your dishwasher or dryer or so forth. So it's similar in batteries. It's not that big an economic issue right now. It's mostly just one of grinding through iterations of testing.
Yeah. Well, if I look at the example of Ford Motor Company with the enhanced polyurethane parts that they have in their Mustang and the F-150, that came about because Ford really kind of pushed its supply chain and said, look, we want to get this. And I've seen the same with aerospace, because, the OEMs in aerospace and Airbus or Boeing don't actually do the formulations. They depend on their supply chain. So I guess the message is for those that are in, key components in the supply chain, doing master batches or delivering systems, they're the ones that really should be looking at this. But the OEMs can also drive this by demanding this kind of performance improvement, knowing that now it's actually available. So let me go to a different question, and this will talk about we'll blend it in. So one of the questions that's coming from a significant manufacturer of equipment is, can graphene material be blended into polypropylene material to improve mechanical, thermal, electrical, and barrier properties? And are there case studies available? Now, on that last one, I'll invite anybody to get in touch with the Graphene Council, because we have a whole host of resources and information about how graphene is being used. But can either of you speak to the blendability or the incorporation, the ability to incorporate graphene into many different types of plastics, polymers, elastomers, etc.?
Yep. Do you want to go, Adrian?
Yeah, go, Mark, and then I'll follow on.
Okay. Well, look, I mean, I'll again try and keep it short and sweet. But yes, it can be blended in propylene extremely successfully. Again, very small additives can have a really big result on everything you've just described. Higher loadings can get you quite significant changes in electrical conductivity and so forth. But we've worked with some customers that have had some very surprisingly positive results, which is the cosmetic side of graphene. That you end up with this beautiful matte finish or a sort of textured finish, which is extremely robust under harsh chemistry, and it actually looks better. So we're seeing these gloss finishes and things like this that are surprisingly good, while increasing maybe the mechanical strength of the part by 50% and causing literally just cents per kilo of polyprop change. So I would say that's actually one of the easiest dispersion type blending opportunities that there is in the world of the polymers. And I would not know about case studies, but as you said, Terence, there's lots of data either through the council or individual users. But I would say another point is that with groups like, Applied has been in the business for a long time and so forth, I think a lot of engineers for different companies probably don't realize how much work has been done from the graphene producer and product side in testing different materials. And so while there may not be a lot in the public domain that you can go see, you may be surprised at the depth of the interactions you can have with a good graphene company, at how much experience they already have and how many years they've already got experience in dispersions into those sorts of products. So I wouldn't keep strictly to the public domain. I would, but there's a huge amount available through companies like Applied.
That's an excellent point. And my apologies, Adrian. I see we're bumped out. We only have 45 minutes. I wish we had a day. And I know we've got to cut the session short. And Frank,
the answer to the question is yes. We do polypropylene master batches, and so yes.
Well, I would encourage anybody listening to get in touch with either Adrian or Mark or both, because they have excellent developmental capabilities, and that's what's needed to make graphene work, is to have it tuned for your application. We have more questions, but we're unfortunately out of time. From my side as the Graphene Council, I want to thank SAE International for this opportunity to speak with your engineering community. And again, encourage you to get in touch with us if you'd like to learn more. This is a real opportunity for massive improvement in engineered solutions. And so we're here to help you if we can. And with that, I want to say thank you to both our excellent speakers for sharing your time and expertise on this subject.
Thanks, guys.
Thank you, Terrence, Adrian, and Mark, for the great discussion today. And a special thanks to the Graphene Council for organizing this session. This concludes our panel session. Thank you for your attendance. Please make sure to check out the virtual exhibit hall and the on-demand technical sessions, which feature more than 300 pre-recorded presentations from the WCX technical program. Of those 300 presentations, more than 70 are focused on design, manufacturing, materials, and lightweighting technology. Thank you again for attending the WCX Digital Summit. Our next set of sessions begins promptly in 30 minutes. Thank you.